Isn't that a lovely image? We have in this NGC 2014 and NGC 2020. This is a Hubble image named Tapestry of Blazing Starbirth. And, well, I mean, honestly, if I'm gonna have to have a background behind me, hello. Why wouldn't I want a Hubble image? They're awesome. Or James Webb image. I got some of those too. Future videos, we'll see what I use. Anyway, this is the inaugural video for the fiction method. And, well, I can't think of a better inaugural video for it than to go through the science fiction presentation I gave some months ago now, but that I gave to my college, to the Society of Physics students there, where I went through some of the ideas of science fiction that I've written, but also just how science fiction is beneficial itself, for including for real scientists, and just the thoughts it can give you for, oh, well, maybe this is possible. So, yeah, gonna go through that. And just so you know, some of it may be a little out of date because it is months old, but also I do intend for some of the specific elements in there, specifically the science fiction elements, to eventually maybe make their own isolated videos that'll be a bit more thorough on that one point, as opposed to this, which just has everything together, essentially. So, yeah, and with that, you're not going to see me anymore. The presentation was kind of meant to be up on a screen there while I'm down here walking around and all that. So maybe those other videos you will be seeing me. For now, though, goodbye, and I shall see you on that. So, as it says on the slide here, this is a discussion on science fiction, a presentation and conversation on the value science fiction presents to real science and scientists by imaginative solutions, consideration of counterfactuals and counter-theoreticals, and simple fun. My name is Jim, and yeah, the October 17th, 2023 is when I last compiled this presentation, and I actually gave it not too long after. Alright, so who am I? Yes, on this slide I've blacked some things out just to make it a little harder to specifically identify me, even though you do have my name. I mean, it's on my books too. So, anyway, I have a Bachelor's of Science in Mathematics and a minor in Physics. I'm the longest active member of the SPS outreach team. For those of you that don't know, SPS is the Society of Physics Students, and it is the specific SPS chapter at the college I got my degrees at. That is also where I gave this presentation. I've written several technical articles, analyses, and presentations, and have also developed various interactive data processing graph generation applets. And just the two long things that I blacked out there, one is just where I work now, which is not totally relevant to this anyway, and the other is just saying where I worked before, which was basically at a science summer camp where I taught the kids the different stuff, and also I wrote some of the curricula even. Well, one curriculum, I should say. Now, in addition to all that, I've also written, well, now 5 novels. This is out of date, because I've written 2 science fiction. We're going to mostly focus on those in the Catherineverse, and 3 superhero fantasy. The one in editing is now out. So, yeah. Alright. And with that, so here's an example of science fiction that I remember being given in like elementary school or middle school, and it's a very basic thought experiment, or just basic image here, of you have a panel in front of you with buttons, knobs, dials, switches, all that, and they're for controlling the constants of the universe, and so I have the universe presented here as well. Now the reason for this hypothetical, for this image, was to try to impress upon me and my classmates that these fundamental constants are so important that if they change, the universe itself will change. So here we have some of those fundamental constants. We have the speed of light, gravitational constant, Planck's constant, vacuum electric permittivity constant, vacuum magnetic permittivity constant, fine structure constant, Avogadro's number, Boltzmann's constant, the elemental charge, and then the luminous efficacy constant. So yes, we're not allowed to change these because things can go real bad if we do. But this is science fiction, so let's actually consider what would happen if they were to change. Okay? But I think a good first place to start with that is to consider, just generally speaking, what would this change appear as? Would it be, you hit a button everywhere at once, it changes. You flip a switch, it changes in just one area. Or maybe you turn that dial and now it actually changes throughout the universe, but on some path, on some specific pattern here, so a gradual directed change. Now, which of these do you think is the most reasonable to try to explain to somebody, to present to somebody in fiction? Well, as you think on that, I should admit I've actually been deceiving you a little bit, because I have this labeled as a science fiction example, but it turns out the idea of a fundamental constant of the universe changing is not necessarily fiction. In April 2020, researchers at University of New South Wales, Sydney, published research supporting prior observations, I want to talk about that, of the fine structure constant varying across the universe. So these prior observations are just, we've made prior observations where it's like, hey, the fine structure constant is a little bit off in this image. Really? Huh, that's weird. How much is it off? Oh, it's in margin of error. Okay, we don't care. I mean, it kind of was like that. We'd have papers that would report, yeah, we recorded that, it was a little different. We found it a little different. But everyone was like, well, yeah, but it's margin of error. We don't need to worry about that. This is different. Because the variances were not random, nor were they a function of time, but of direction. Meaning, we had that gradual directed change. This is very significant because it's one thing to be like, oh, it's just a random value that's off. That's just margin of error. But when there's a pattern in there, because you have that explanation, it's just random error. How do you explain away the pattern, though? Because there's now order there, and you need to explain that away. And I know it's been a few years, I don't recall seeing anything to explain this away. But it gets even better. Researchers in the US studying X-ray emissions made the same discovery and also published that same April. And by same discovery, I mean they also found the fine structure constant was changing along a direction, and hey, it was the same direction. So we have two different studies, independent groups, that found the same thing. That makes it even more significant that you really would have to explain away this pattern. Alright, so now what does it actually mean for the fine structure constant to change? Well, we need to understand what the fine structure constant is. It relates to electromagnetism and the values of the speed of light, Planck's constant, vacuum electric permittivity, and the charge of the electron, all of which were on the list earlier, the list of fundamental constants, and you can see the formula for alpha there. Alpha being the fine structure constant. So, sufficient changes to this constant can upset the interaction of electrons with other charged particles and photons, which would mean the whole of chemistry can be altered. Okay, so you start changing this, and the binding energy between molecules, or rather within molecules, can be different. That'll make some molecules easier to form and some molecules harder to form, which would disrupt basically everything. Maybe not so much in stars where you have hydrogen, helium, and lithium, but yeah, anything larger like planets, no, the existence of planets would be different. And here's where it gets kind of wild. Technically, this is the easier thing to consider. Chemistry itself changing is the easier one to consider. So, a little bit of an aside, comes back though, locality is a critical component for the theories of relativity. In this context, it just means a phenomenon is not dependent on its location in the universe. So, picture this, thought experiment. You have a box with a button and a light bulb on it. Some phenomenon happens in the box when you hit the button, but what happens is you hit the button and the light bulb lights up at a specific brightness and a specific color. Well, you hit it, and anywhere in the universe, it should be the same color and same brightness, okay? That's basically what locality is. Here's the problem, though. If the fundamentals of physics change, then the phenomenon can and even will have to differ, which would mean locality fails. So we hit that button, and now because we're somewhere else in the universe, where the fine structure constant has a different value, the brightness of the bulb might be different, and the color of the light it produces might be different. That's a definite problem, right? Now, fortunately, if you're thinking, oh, we have to start throwing out textbooks, or oh, we have to start changing no, we're not there yet. This is just two observations, still kind of a big deal, but we'd need many more observations. We'd want to have some understanding. And also, we still use Newton. We still use Newton's laws. Why do we do that? Theories of relativity replace that, right? It's because on this scale, they're still appropriate. Like, for just us walking around doing normal, everyday things, Newton is fine. Newton is right. Even if we find that locality does fail, which would knock out the theories of relativity, if we found that, it still is on the scale that we mostly operate at, which could be the galaxy, or even the galaxy cluster. I don't know what the scale was for these changes in the fine structure constant. But even on that large scale, relativity may still be fine. So we would probably still continue to use it because it would be correct there. It's only when you go beyond it that it's like, okay, now locality is failing, so we need some new physics. But it could very well work out like that if this all does prove to be an issue. And another thing to consider is Why are they still the theories of relativity? They're not the laws of relativity, and they're about 100 years old now. Right? So why is that? It's because they still have not been firmly proven. Okay? But on top of that, we don't use what Einstein wrote. They've been changed because there have been other observations that don't quite align, but people figured out what the modifications were necessary for relativity to be updated, and now it accounts for this observation. I don't know if you can necessarily achieve that with locality because it's kind of a significant one. I mean, it literally does underpin some of the concepts to the theories of relativity. So you might not be able to just modify that to fix it all, but it still is. It is a living thing at the moment. It's not set in stone, so we can make changes that may account for this, or it'll just be right in a very large zone, and outside of that zone, well, now we have to use something different. There's nothing wrong with that. That's actually how science and physics has worked for a very long time. Okay? So, yeah. And now for something else. Turns out fine structure constant is not the only constant that has some issues with its value. So the Hubble constant is the rate of expansion of the universe, and so it is of critical importance to cosmology, and naturally when you have something that important, you try to have multiple independent methods of measuring it, and we have devised various of those, but they provide us with different values. One gives us 67 kilometers per second per megaparsec, the other gives us 74 kilometers per second per megaparsec. And those are the two most confident values from those measurements. So looking over at the graphic here, this is not accurate because I just use normal curves for this. But this is how measurements actually work. Where we have a measurement and we just have a confidence function like this, or technically a probability distribution function. Where it's like we're most confident that the value, the peak of this distribution, that's where we're most confident. So we're most confident at 67, we're most confident at 74. Okay? But technically it could be a little bit off. That's what margin of error is. It's a certain width on this function, probability distribution function. Now, as long as there's enough uncertainty to these, as long as those functions are wide enough so we've got this overlap, there's no problem. Because the true value can just be, in that overlap, because it's within the margin of error for both, okay? Before going on, just because I'm not sure how many people may be aware of what these units are, well, I think you know kilometers per second. But megaparsecs, a parsec is about 3.25 light years, so it would be 3.25 million light years. So we're talking about adding, just rounding it off, 70 kilometers to 3.25 million light years every second. Technically, that's not much, but when you're talking about distances that are in the millions, tens of millions, hundreds of millions, even billions of light years, and over millions, tens of millions, hundreds of millions, and billions of years, it does add up. So it is actually significant, but it is just on our scale now, we don't need to worry about that too much. And also the 67 kilometers per megaparsec, that value, that comes from the Planck data, which is cosmic microwave background radiation. So it's very old. And this is relevant in the next slides. The 74 kilometers per second per megaparsec, that value comes from observing Cepheid variables, just a kind of star that we can predict certain things on. So when we see differences, we can figure out that, oh, this is what's going on. It's one of those things. Okay. So over time, these measurements have been improving, the Cepheid variable measurement and the Planck data measurement. But they're not approaching a central value. So those distributions, instead of converging onto a central true value, instead they're getting taller and narrower. So getting more and more confident in 67 and 74. So there's less of the error in between that the true value could be at. This is known as the Hubble tension, okay? So yes, this actually has its own name, that this issue of which value is it, has its own name. Well, in May 2021, researchers at the University of Michigan published a novel solution to the Hubble tension. Maybe the Hubble constant isn't a constant. No, seriously, that's basically what it boils down to. They grouped the measurements by distance, so Cepheid variables at this distance, CMB all the way out there, and they can have others because there's many Cepheid variables out there. But what they found was that the value changes with distance. Now, we don't know why. The mechanism to explain this, we don't know. But it took some 20 years from recognizing the Hubble tension to this analysis. When I was doing searching, it was about in 2001 that I first saw the Hubble tension mentioned, okay? It took 20 years for somebody to finally be like, hey, you know what? Maybe the Hubble constant isn't a constant. Maybe that explains things. Why don't we do this, binning of the measurements by distance? Oh, look, it does in fact change. It increases as we get closer to present day and present location. Yeah, it must not be constant. I mean, it may not have taken 20 years, to be fair. It's possible that there were papers that came out earlier that came to this same conclusion, and I just didn't see them. But it still is. It's like, how did it take 20 years for this? This is part of my point about science fiction and counterfactuals and countertheoreticals. Because just the statement, the Hubble constant is not constant, for some, that would be a counterfactual. The Hubble constant is a constant. It's in the name. Well, maybe it's not. Maybe we shouldn't consider it that way. That's a counterfactual or a countertheoretical, depending on how you want to look at it. So that's why science fiction, it is useful. Because sometimes you need to think outside the box. You need to think of something different than just what you're reading, than just what you've been told. And sometimes that's to find a real solution. Other times it's just to expand. Just to, hey, what happens if we consider this thing that we've always been told is impossible? That we've always been told is wrong? What happens? Well, you may end up with hyperbolic geometry. And I'm serious, the part of the origin of hyperbolic geometry was, hey, this axiom of geometry? Why don't we just ignore that and try coming up with geometry without that one? And it worked. So what is science fiction? Now, I don't have a background in literature. I do a lot of writing. I write literature, but I took one English course in college. I had more in high school. But it's like, that's it. So the answer I'm going to give you is not necessarily the answer that an English department would ever give you. But I'm okay with that. To me, I consider it, and there's more to it than this, but I consider it to be well-ruled, reasonable, and explainable. Okay, these are very critical components to it. So in science fiction, to use the laws of physics as an example, they can and should be maintained, bent. You can break them, but if you break them, you need to heal them. Okay, so broken and healed. And the significance of this healing and explainability is how I discern it from fantasy. So if you have a fantasy story, you have a rock that suddenly lifts into the air. You can say it's magic, and that's the explanation. And like that's as far as you go. The actual explainability of it is not necessary. It's magic. Whereas in science fiction, that same rock leaps into the air. Okay, what was its thrust mechanism? How are we conserving momentum? That went up, so what went down? We need to start answering that. We need that explanation there to make it science fiction. Because otherwise it is just, don't pay attention to that rock. Don't try to think about it. I don't want to do that. I don't want to pull you out. We're now like, wait, rocks can't float. So you need something there. Now, in fantasy, you can still explain it. You could get into exactly how the magic works, and that can be helpful because that can provide healing to whatever it is you're breaking, and it can thereby ground the story. And to me, part of grounding is it does bring the reader or viewer or player, depending on, could be a movie, could be a video game as well. It brings it into, it's like, okay, I understand this. I'm getting into this world. It makes sense. I am figuring it all out. So now I want to focus on that whole well-ruled. What do I mean by that? Well, are rules a problem? I guess is one good question to ask and answer. Because some people I could see being like, well, why do you want to have all these rules? Because it's like, you're building this world. This is your world. Why have these rules here that you have to obey? And that's a fair question. I can see some being like, when you put yourself in a box, that may be limiting. But remember, you're the one building the box. I'm the one who made the rules. I'm not having to go by somebody else's rules. But the structure of the box can actually be helpful. Because it helps you maintain the structure of the box and therefore also the story. So restrictions can actually enable you to be more creative and avoid confusing nonsense even. And I've had this happen in stories. There's one in particular, I actually came up with 2 solutions to problems before I had the problems. Which was great, but it was exactly an example of that, where it's, even though I was restricted, I had to be within certain rules. It turns out I had already acted within those rules, already thought out something within those rules that worked for me later on. In one case, it was just a throwaway thing that I set up chapters before. Well, it wasn't really a setup. It's just hey, I want to have these 2 characters continue to converse some. I want to continue some interaction there. I need a reason for them to do that. I'll give it this reason, that this dude has to carry this thing with him. All right. So many chapters later, that thing he's carrying with him, he can use that now. That's a resource. I didn't plan on that, but it worked out. And to me, that's exactly what I mean here. was like I couldn't just have him randomly pull the resource out of nowhere. No, he had to have it with him already, and it just so happened he had it with him by accident. But it worked out very well. And then another example in that, although it's not obvious, I had thought out how this one character would be introduced to another character in the story. It's not how he is introduced in the story. But in that introduction between them, the main character of the story, who's relating this, he learned something. He learned some really neat things from this guy. I figured that out well before I actually wrote it in the story. And I ended up writing in the story right next to where it's like, oh, I have this problem. Hey, that thing I learned, it'll solve my problem here, or at least help solve it. It's like, that's what I mean by this, where it's actually encouraging me to be more creative and figuring out how I can connect these things all together so it makes sense. So it's not just, oh, he's pulling things out. No, he already earned this knowledge from somebody else. And then his explanation of how it works is how it works. So it actually does work out very nicely to stay within these rules. I don't need to go to a Deus Ex Machina. I don't need him to just be a spontaneous genius. No, he can learn it from somebody else. Nothing wrong with that. And also can help make a character more relatable, more believable as well. By the way, I didn't go into all this when I actually gave the presentation. I tried to keep it a bit shorter, but since I'm at home just in front of a mic, I am going on a bit more. But it's like, I like this stuff. I enjoy this stuff. I want to talk about this stuff. Alright, so let's move on now, because we've covered some science facts, some little bit of science fiction in there, and also science fiction genre, if my mouth will work for me. So next up, let's start, actually applying some science fiction and having some fun. So it's time for Spaceship Building 101. Alright, remember I delivered this to a college, so I'm going to have some college-related jokes like that. So, based on the previous section on science fiction, remember we need to have the goal of having be reasonable and explainable for the design mechanics. And we also need to make sure that this box we're operating in with the rules is something others are going to be able to understand. Now, a good first step for trying to design a spaceship is knowing where it's actually going to work. What is space? Or more specifically, what is interstellar space? Okay? Ask yourself that question. What is it? I mean, you may already know. Please don't just look it up, because I will tell you, but it's like, what is interstellar space? When you look at the term interstellar space, what does that tell you? Now, some of you looking at it might know, oh, well, that means the space between stars. Okay, that's good. But where's that line? If I gave you a map of the universe, or let's just say a map with a radius of 5 light years from the sun. Okay, so that's actually going to include at least one other star. Where is the line for the sun, the solar system, and interstellar space? Where's the border there, okay? Do you know? Well, let's tell you. Interstellar space is defined as the space beyond the heliopause of a star. How many of you know what the heliopause is? Right? Well, stellar space, according to this definition, is where the solar wind dominates. The sun is constantly ejecting a bunch of charged particles that they have, and this is actually kind of relevant, high energy, but a low density. The solar wind has a lower density, and it's constantly pouring those out in all directions. Okay? That's the solar wind. So where it dominates is dominant. That would be stellar space by this definition. Well, the sun and stars are not the only source of these. There's also the interstellar medium, which is, again, it's just particles, like the solar wind, but they're not as high of energy, so they're a bit cooler, but they also have a higher density. Well, when these two hit, the stellar wind, the solar wind, and the interstellar medium, when they collide, they actually strike against each other and kind of stop moving. They balance each other out. This is what the heliopause is. Okay? How many of you, going back to the whole, how do you know what interstellar space is from the term? How do you know what the heliopause is from the term either? I'm saying we have these jargon terms here, and I kind of doubt many people know them. Okay, which is kind of a problem, because when I'm writing a story, I want somebody to understand what I'm talking about. And I also have these other considerations that are now down here. Is interstellar space what people working in it are actually going to call it? It's like, we're not talking about necessarily scientists, we're talking about, tradesmen, craftsmen, and such, that's just where they are. So are they going to use that jargon constantly? I doubt it. It's not a colloquial term, and I would think that just normal people working there, not scientists, they would come up with a colloquial term. Is this most descriptive name and definition? it really isn't. Interstellar space doesn't at all connect you to the heliopause, but there's also, the heliopause has a thickness to it. So it's like, okay, you drew that line on that map. Okay, well, is the boundary the inside of the line? Is it the outside of the line? Because there's a thickness to the line. Or is it somewhere in the middle of the line? It's like, where is it actually? The heliopause is a wide area. It's not a single firm line. Which, on one hand, yeah, that's not something we can fully get away from in the alternatives that I'm going to suggest. But it still is, just the heliopause itself has a width. Which is it? Inside, outside, somewhere in the middle. And then there's also, how is it measured and determined? Okay, well, for this, you would need a particle detector, actually potentially multiple. That's a specialized piece of equipment. So you'd need to be trained in how to use it and also trained how to maintain it. Right? Because, and what you'd be doing is you'd be capturing particles to measure them, not for necessarily what they are, but their energy level. Because what did I say earlier? Solar wind, high energy, low density. Interstellar medium, high density, low temperature, low energy. So you'd be measuring for those two things. And when you see a shift, that's when you would know whether or not you were in interstellar space or stellar space. And technically, if you're seeing a mix or just they're not really moving, you'd know you're in the heliopause then. Alright, well, let's consider some alternatives. So going off the whole, where the solar wind dominates, because really, I think the easiest way to define interstellar space is to define stellar space. So there's where the solar wind dominates. Well, there's also dominant gravity. Stars have gravity. Everything has gravity. So it's like, okay, when the star's gravity is dominant, you feel, you can measure that you are being pulled towards that more so than anything else in the universe. Okay? Well, that can work. There's also, though, the star's electromagnetic field, which I'm depicting as being larger here because the electromagnetic force is technically stronger than the force of gravity, but, it's whatever. It doesn't matter one or the other. The idea is we could do that. Okay, so when the electromagnetic field that you're measuring, it's the strongest for that star over everything else that you would be measuring in the universe. Okay. Here's a problem with both of those. They're kind of hard to measure with directional specificity. Right? It's like with gravity goes through everything. So how do you know that measurement you're making, it's for that star and not a different star? And also, what if it is, you want to measure for that star over there, but this one's closer. There's another one that's closer, and that's gravity is dominant. Just because or at least it's more dominant than the one you're actually trying to measure. That's a problem. So you may want to know, okay, how far am I from the stellar space of that star, even if you're next to a different star. Same thing with the electromagnetic fields. How do you filter down to make sure, nope, it's that one I'm looking at, not this one? Okay, gets a little tricky. Well, here's my actual solution in my stories. Dark space. Now I want you to just take a moment and think, based on what I've told you, what do you think my definition is of dark space? When I gave this presentation, I'm giving you time to think. When I gave this presentation, I asked this question. I also asked, what is interstellar space? And the answer I got for interstellar space was very, very wrong. It was very incorrect. He tried, though. When I asked somebody else for what the definition is of dark space, he gave it to me. He knew exactly what it was. He wasn't confident in his answer, which is fair. It's a new term, but it still is. He was able to figure out, just from the name of it and what I've been talking about, just by the name, what it is. And just sticking with the term a little bit longer, it's a sufficiently colloquial term that also identifies its meaning. It's a lot easier to say dark space than interstellar space. And it does describe it, and he got it right. It's the region lacking a dominant source of starlight. So light of the nearest star is below some critical threshold, which I have illustrated here with these graphs. This is just inverse square law. That's how the energy of the light of a star would diminish. And I have different examples here, but then that critical threshold, that green line, that just goes across. And when you are above that, so it's brighter than that critical threshold, well, now you're in the stellar space of that star. And here's something else that's really cool about this measurement. It can be done today. You just need a telescope and a light sensor. In other words, a camera. And it's like, I've got cameras all around me because I've got my current phone, I've got old phones because I don't throw things out. I've got my nice Nikon camera there. I've got my laptop with its webcam. I've got some dead laptops over there with their webcams. Light sensors are all around us. So this is something we could do today. It wouldn't be very relevant compared to some other measurements because we're not exploring in interstellar space, but still we could do this today, and anyone could do this. That's a lot better than the particle detector that you would need for interstellar space. But it's also coming back to a dark space. It describes itself, and I do think that that is, as I say there, a sufficiently colloquial term. That those working in it, those living in it, that's what they would say. That is how they would describe it to each other. That, oh yeah, it's in this place in dark space. Not it's in this space in interstellar space. Okay? I think that that would in fact be the case. It would be more approachable, more common, more so the vernacular. So now that we have an understanding of where the ship is going to be operating, we now need to think about, okay, how do we power this? Because it's dark space. We don't have an external source of energy for this thing, all right? Not one that's reliably just always there. It's not, a gas station every 5 miles kind of situation here. So how do we power it? Since you need that external source of energy potentially. Well, before we get too deep into that, we need to consider what the purpose of the ship is, and is local generation necessary? Because if we have the ship like always going between space stations, always going between planets, then we do technically have that external source of energy. There's a huge distance between them, but we do technically have that. So you could go with a storage mechanism instead of generation. Okay? But that's only if we are doing that. If we're exploring dark space, well, now it's different. Now we do need some ability to generate. And one way to think of it is this. A gallon of gasoline has a lot more energy in it than a gallon of lithium-ion battery. Storage mechanisms are going to have a lower energy density than a actual straight-up fuel, than just straight-up energy generation. That's just how that is. There are some cheats there, but I'll get to that when we get to energy storage, some examples here. First up, though, energy sources. So there's chemical, like gasoline. There's nuclear fission and nuclear fusion. And now, just a little bit of an aside, because I did do this during the presentation. I know it's not going to be chemical, but between nuclear fission and fusion, which of these energy sources do you think is better? Okay? Which do you think makes the most sense to have on a spaceship? Okay? Now, obviously, for the presentation, I asked people to raise their hands and all that, to see what people thought. Can't do that here on YouTube. Well, if you're thinking it's nuclear fusion, you're wrong. It's actually nuclear fission. And here's why. Fission is a spontaneous event. Okay? If you had a hunk of nuclear reactor fuel sitting near you, for one thing, you're in trouble because of the radiation from it, but it just is pouring out that radiation. It's just pouring out that energy. It just does that because it exists as something that does that. Nuclear fusion, however, is stimulated. You have to pump energy into that in order to have it do anything. Okay? That fuel sits there, nothing's going to happen. Well, that's a danger, because remember, going up on the slide, there's no reliable external source of energy. What happens if you don't have the energy on your ship to ignite nuclear fusion? You're going to die. It's like that is legitimately what's going to happen, because if you fail to ignite it, you no longer have power. So you'd either need a very robust energy storage mechanism behind it, or you should just have nuclear fission as the backbone. You could potentially have both on a ship. In fact, in my science fiction, I think if a ship did that, for one thing, it would have to be really, really big, because fusion can put out a lot of power, and it's technically you're just triggering nuclear explosions that are small and kind of controlled, but you're still doing that in your ship. Doesn't seem the safest. So it's like it would have to be a very big ship that can actually use all that power, or a space station. Space stations could also have both, because it's sufficiently large it can handle all of that. But just on its own, fusion makes no sense for a spaceship. It really doesn't. Alright, so with that, now let's get to energy storage. Energy storage options. So we got capacitors, which I like. They charge fast, they discharge fast, they're pretty stable, but they don't have that great of energy density. Yeah, there's supercapacitors, but it's not great. Batteries, much better energy density than capacitors, but they're slower to charge, slower to discharge. So those aren't ideal either. And it's still, we're talking about not great energy density compared to just an energy source. Now there's chemical energy storage, and by that I mean things like artificial photosynthesis. So that's, You take carbon dioxide, you take water, you mix them together, put in some energy as well, boom, you get things like propane or methane for natural gas and octane for gasoline. And yes, this is actually something being explored. It's just it can take a lot of energy to actually make that. But it's like that's an option. But again, it's we're putting that in versus to use natural gas and gasoline as the example versus the natural processes that make it over tens of thousands of years. Because I think it takes that long versus, in a lab that takes a week. So, there are trade-offs between them. Well, then we also have energy storage, something that sounds like it's science fiction, but really isn't. This is real. Superconductors. If you have a ring of a superconducting material, so you're putting electric current on there and it just goes round and 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 round, it goes around and round, never losing energy because there's no resistance. That's why they are superconductors. No resistance, or very, very minimal. And I don't know how much we necessarily use them for that, because they do kind of act then, like you can discharge those things real fast. So they give you better energy density than a capacitor, but better charging and discharging than a battery. There are some issues there as well, but we can ignore some of those and say, yeah, these are room temperature superconductors. Because it's science fiction, we can do that. But, I don't know. I mean, everybody does superconductors. I mean, everybody knows that. Is it really that fun of science fiction? I don't think it is. So I came up with my own answer, my own solution. Superparamagnets, which is going to be a lot of fun for me because I got a speech impediment and it's going to be hitting me with that word so many times, so forgive me. So what is superparamagnet energy storage? I'm going to try to talk slow, so hopefully I can get through this without tripping over my tongue too much. So it is a fictional invention of mine, meant to bend physics, not break it, because paramagnetic materials, they do exist. And what happens is, when you expose them to a magnetic field, they actually will take on one of their own. But they're not a permanent magnet, like iron is. But they will still take on a magnetic field. Now, for superparamagnetism, I'm just trying to imply with that it's a very strong reaction to that external magnetic field. So let's just say it would be 1-to-1, okay? That's not unreasonable, it's super. So here's a graphic here where the external magnetic field would be the straight lines, while the induced one is the ellipses. Technically, it should actually also be straight to connote the same power, but I need to demonstrate in the illustration. Alright, so how do you use that to store energy? Well, here we have this next graphic with this other object there that's essentially a specialized keeper. And to quickly explain what a keeper is, the energy of a magnetic field, actually the energy for any field, is stored along its lines, okay? So it's whenever something crosses those lines that energy can go in or out of the field, okay? Well, if you just have a magnet sitting there with the magnetic field going out in all directions, there's a lot of things that can cross through that, so it's possible for it to lose energy that way. So that's why a lot of magnets, especially like horseshoe magnets, since the poles, there's a gap between them, but they're very near each other, you want to put a keeper across them. And if you do that, what will happen is the magnetic field of that horseshoe magnet gets pulled into the keeper and stays there. And the thing is, it's in a solid material now. There's nothing crossing those lines, so there will be very minimal to no energy loss. Now we want extremely high permeability. That helps ensure two things. One, that all the field lines will go through the keeper, but also that there will be minimal energy loss. And by the way, just to further clarify what a keeper will do here, and I've done this. I did this with a group of kids. They loved it. It was awesome. I had something that, had a bunch of like iron filings in it. It was sealed, clear container, so you could see them there. Put them next to a horseshoe magnet. So they were pulled up and held against the clear plastic so the kids could see. And it's like, yeah, kids have probably done that. They've probably seen that. I then took that keeper, though, and I put it on that horseshoe magnet, and all the iron filings fell. Because now the whole of the magnetic field got pulled into that keeper, which was just a piece of iron. But still, did that immediately pulled in so it wasn't there to hold the iron filings up anymore. Pretty neat, right? Well, in this case, the geometry is kind of changed, where the keeper is more so shaped like the horseshoe, and the paramagnet material, that's a simple bar, or in this case, it's a square. So because the magnetic field is going through the keeper, it's like feeding back into the paramagnet to actually store and protect the temporary field for an indefinite length of time. Now, why did I actually come up with this? Well, I came up with superparamagnets because I wanted a counterpart to superconductors, and one thing that I've seen when going through different science and technology press releases is there's a definite interest for various electrical or electronic-based technologies to find their magnetic counterparts, because in some cases the magnetic counterpart can be superior. One simple example of that, well, simple to describe at least, is spintronics versus electronics. Electronics use traditional electricity, which is based on voltages, so energy levels of the electrons. While spintronics uses the spin of the electrons, which is a fundamental property of electrons, so it's always there. And spin is also where magnetism comes from. Okay, so if you've got everything aligned, all the spin of the particles aligned, the spin of the electrons aligned, you'll actually produce a magnetic field. Putting it another way, electrons always have a magnetic field to them, okay? But in many materials, like in a paramagnet that's just sitting there, they don't align. So there's no larger, constructively built magnetic field. But if you get them to align, like in a permanent magnet, now you have a stronger magnetic field that does actually reach outside of the object. Okay. So a superparamagnet is going to store energy rather than in a current, like a superconductor, stored in that electron spin alignment. Okay, that I just described how magnetic fields are formed. So we got this image here, this graphic. So current on the one side for superconductors, and this is, well, it's not going to be completely accurate, but it's not completely inaccurate. The way you actually get superconductivity is with something called Cooper pairs. Now you might think that because it's the electrons, they have the same charge. They don't want to be near each other. They resist. Well, no. In superconductors, they will actually form what are called Cooper pairs. And Cooper pairs will, the interactions between the electrons in that is what allows them to travel with little to no resistance. Okay? So yeah, that's how superconductors work. And then my superparamagnets, now we've just got the spins there, and they mostly align, but they're not all perfectly aligned together. And that's fine, because it'd still be energy there, because it doesn't even want to be that much aligned. Okay? So both of these, there is some energy being stored. Now, a benefit to going with this, using electron spin alignment, is a protection from overcharging. Okay? So you may not realize this, but superconductors actually have a limit to the amount of energy they can store. And the graphic above kind of exposes this. Not perfectly, but is kind of there. So, for one thing, that current, those Cooper pairs have to have some sort of potential energy. Otherwise, if you hook it up and there's no potential energy, well, there's no energy you get out then. So they need to have that. There needs to be a voltage compared to whatever it is you're trying to power. Well, the issue with the overcharging is if you put too much energy in there, then you have a lot of these Cooper pairs going around, and they're potentially going to be bumping into each other. And an analogy could be, you got a bunch of cars on a highway just going round and round and round and round. What happens if they bump into each other? They slow down. Okay, they're going to slow down, potentially be completely damaged in the case of a car, but it's still, they're going to slow down, so you actually can lose energy. Those strikes against each other is going to be spontaneous resistance, essentially. Okay? So, if you overcharge a superconductor, technically it stays a superconductor, but you will get resistance and energy loss. You can't do that with electron spin, though. Okay, it's like they get aligned, they're perfectly parallel aligned, and that's it. There's just a maximum limit. You can't push more energy into that. It's stable, it's solid state, because spin is just a fundamental property of an electron. Voltage isn't. And voltage is what you're actually going to be pulling out of the superconductor, well, along with the current, but it's like the voltage matters there. But that's not normal. That's why in computers, you have volatile memory, where if energy is lost, if power is lost, then the data is lost as well. Because those electrons that are storing the information at their voltages, they're constantly being pumped up. They're constantly being knocked back up into that voltage. But they don't want to. They want to give that up. They want to fall down. And if they do, you lose your data. But spin, in spintronics, so long as the electrons are sitting there and they don't turn their spin, the data is still there. It's perfectly fine, perfectly protected. It is inherently non-volatile. It is inherently solid state and stable. So that is another advantage that superparamagnet may have over a superconductor. Now another is how you can charge these things. Because in theory, pull that paramagnet out, when you buy a powerful external magnetic field, like say a star or a planet, you do that, it's going to have that magnetic field imprinted on it. That's what it's going to take. And then you slide back into the keeper, and then over time, whenever you need the power, well, you just slide out a little bit, expose that magnetic field, and that's what you pull the energy out of then. Pulled from that exposed magnetic field. And I do speculate, I'm pretty sure that there would be some heat loss, well, some heat produced from this, that it would be exothermic. Just that as the electrons fall out of alignment, that would release some heat. And one other thing I will add to this, because, okay, well, how do you charge up a superconductor? Well, you'd have to give it an electric current, and with some voltage there. You would need to plug it into the wall, essentially. Well, you would also be able to do that with a superparamagnet, because you would need something that can produce a magnetic field near it. Well, the same thing is also what would absorb the energy out of the magnetic field. It's just when you're discharging, it's like, okay, pull the energy out of the magnetic field there. And when charging, you would have that same thing, just produce the magnetic field that then the paramagnet tries to induce its own. Okay, tries to copy onto itself. So it would actually all work together. And you could still plug it in and charge it. You wouldn't have to, hey, where's a star so we can fill up? You wouldn't have to do that. You could just plug it into any old power source. Alright, so now that we've got power figured out, let's start figuring out thrust, engine design. We need to make the ship go, after all. Well, here are some options. We got chemical rockets, we have ion drives, and we have nuclear engines, which I think there's two different things that are named nuclear engines. I'm going to reference something that I saw in a book that I wish I knew where it was. It's somewhere in the house. But it's pretty neat, and it's from like Cold War era, so it's a bit old, but it still is a really neat idea. So with chemical rockets, you have a fuel and an oxidizer. So I mentioned gasoline earlier. That would be gasoline and oxygen. Okay, that's how your car engine works. Obviously, we're not using gasoline for chemical rockets, but it's still same kind of pairing. Well, an issue with chemical rockets is you need to store the fuel and the oxidizer, and the mechanism to do so is going to be kind of bulky. I mean, think about the space shuttle. You've got that huge external fuel tank that's bigger than the shuttle itself. Multiple people live and work in the space shuttle on missions. And this thing has to be bigger than that. Okay? So yeah, it's big. And that's kind of a problem. And so what happens during launch? That gets dropped away. The Apollo missions, what happens? Because you have multiple stages that have their own fuel storage. They drop away because it's bulky. It gets in the way. It's so much more mass. You don't want to have to carry it all the time. All right? So not ideal. Ion drives. Well, they're better. They use fuel and energy, and fuel is ions and then electricity to throw them out in a specific direction. So that does make them more efficient than chemical, but still, you got that fuel that you have to store, and that mechanism for storing is going to be kind of bulky. It's going to take up space that cannot be used for anything else. And then there's nuclear engines. So this is, it uses a fissile material, let's just say uranium as the example, and an ablative material. So what that means is you got the fissile material there. Where it undergoes fission, so it releases a particle of radiation. Whether that's an actual subatomic particle or a photon, it releases it. Well, that's going to have so much energy to it that when it hits the ablative material, it ablates it. It hits it and ionizes it. So now a particle of that material is kicked off from it, and that will fly off in some direction. That is what produces thrust. So it is kind of analogous to an ion drive, except you're generating the ions on the spot and through this nuclear reaction, as opposed to just having some fuel, as I referred to it earlier. And you would probably want some sort of electric net that an ion drive will use to direct the ions in a specific direction. You'd probably have something like that as well, but it still is, instead of the fuel potentially being a tank of material that you can make into ions, it's a hunk of metal or something, some other ablative material that's just doing that. Now, of course, you still have similar kind of concerns here of you have to have this material. You're talking about nuclear fission here that kind of has to be exposed. I mean, you can't have this completely contained like a nuclear reactor. You need part of it exposed, at least to space, so that, it goes out. So, yeah, it's not exactly going to be the most ideal thing to work with, but it should at least have some good density. Well, I didn't use that. I didn't use ion drives. I didn't use chemical rockets. No, what I use is optical thrusters. Because there are certain advantages here. One is it uses energy only. And we've already gone through how you can store energy. And also options for generating energy. It's just I've not explored that too deeply yet in my science fiction. But still, it's just using energy. That's it. There's no fuel. So there's technically no other storage that you have to be concerned with. It's just, yep, plug it in, we're good. It also can be a much more compact design and involve fewer parts. You, in some cases, just need the light source. That's what it is for Generation 1, which, as I described here, it's basically a huge laser pointer. And it's easily directed and simple design and concept. Okay? And in my Catherineverse, they actually are still used as maneuvering thrusters. Generation 2 are on a way better for main engines. They produce far more thrust than this. But this is a good place to start. And once you have them, put them everywhere on your ship. So that's how you can, get it to turn, get it to shift left and right. I mean, it's like they are perfect for that. So now let's get to Generation 2, which there's a fair bit going on with Generation 2. So with this, the emitters are now actually on a curved surface, which is a greatly increased area than for the light to be produced. I kind of want to go back, but I won't do it. But in the previous one, you basically had that one flat surface, right? That was it. Well, here, because it's curved, now you potentially have, just think about the circumference of a circle versus its radius. Even at half a circumference, well, half the total circumference, and you've cut out a section, that's still a lot more than just the radius or diameter of that circle, right? And yes, I know technically it's a sphere here, but I'm showing you a circle, a half circle. So it's like that's a lot more surface area. So we're talking about a lot more optical power being produced there. And that makes it very good for main engines, but it's not so good for redirecting because it's kind of big. You can't really grab that thing and just turn it around. Oh, and I think I forgot to mention that, yes, there's a reflector. So all of the light is being aimed on that reflector that then aims it outside of that hole. So because technically those forces should largely balance. The optical power from all those emitters would balance out in some ways. Well, the reflector makes sure that all of it goes in one direction, so you end up with a lot of power then for your thrust. Now, there's something else that we can do here with this design. Is going back to that nuclear engine. What happens if we crank up the optical power? In theory, you could actually have it start sacrificing ions from the reflector. You could have it start ionizing the reflector. Well, what do you do with these ions? You could make it into an ion drive. It's like this would be a good way to have emergency thrust, because the ions have more mass than a photon, so that's going to produce more thrust for you. But you are damaging the reflector. It'll still work, but you're still damaging it, so emergency thrust only. But still this is science fiction. I don't need to use an ion drive. I can use something better. I can use magnetic reconnection for increased momentum. And the two sources there, it's only one of them I think that mentions it, but can be 10 times the thrust of an ion drive by using magnetic reconnection. Really neat, right? So what is magnetic reconnection? Because it's not that well known of a phenomenon, I think. It is kind of what it describes. So you've got the magnetic field lines. Well, you can pinch down a magnetic field, and this does happen. The Earth's magnetic field has this happen to it when the sun is particularly active and it's spewing out its solar wind. Because those charged particles have their own magnetic fields, and they'll start compressing the Earth's magnetic field. Well, what can happen is it will compress it enough, it pinches down enough on the Earth's magnetic field that it kind of gets an hourglass shape. And if you keep pressing, keep pinching there, it'll actually cause those field lines to disconnect. So instead of that hourglass shape, you'll end up with two what appear to be separate lines. Technically, it's the same line because it's the same energy level. But you do that, now one is going to go to a circle, and, well, technically the other will also snap back to being a circle as well. But here's the thing. Because those lines, once you disconnect, they reconnect to themselves, so you get that circle. But something I said earlier, fields store their energy on the field lines. You just disconnected these lines and then they reconnected. The reconnected lines are shorter, which means that there's technically a loss of energy to the field. The energy isn't actually lost, it goes somewhere else. It goes to launching that circle way the hell out there, and at very high speed. Okay, and I guess one way to think of it, and this isn't perfect because I don't think it actually does work this way. Well, maybe it does. A drip falling from a faucet, because the shape of those field lines is actually going to follow the edge of the water for that. Where it gets pinched down as the drop gets heavier and heavier and heavier, once it disconnects, the total surface area of the water there actually reduces. Because the drop pulls into being a sphere, or nearly, and it also, the portion of it that's still connected to the faucet snaps up to itself, right? So the surface area reduces. Where does that energy go from that loss of surface area? It technically would be launching that drop down. I don't think that's actually what's going on there, but magnetic reconnection, using the droplet as an analogy, that's what's happening. That loss of energy would launch that droplet down. As I said, though, I don't think that's what actually happens in reality. It would be kind of funny if it were, though. So yeah, that's how magnetic reconnection works, and it is more powerful. So, and it makes a lot of sense because you're damaging the reflector. You want to be as efficient in using those ions as possible. This is an emergency situation, and if you damage that reflector too much, you might kill the engine. So, like, it might not be usable until you put a new reflector in. Though I guess I can mention I do have it canonically. The engines actually have spare reflectors in there, and are designed so you can change them out if need be. Anyway, Generation 3. So this is very much just a step up from Generation 2, where now there's multiple emission layers, which is nice because that multiplies your optical power, multiplies the thrust. But they're much more complex and much more expensive. And you require a very precise alignment of these elements. Because, I'm just trying to, it's hard to think of the best analogy for this, or best explanation for it. But it's basically, if an element produces light of a specific color, it will also absorb light of that color. Okay? Now, it kind of is accurate. So if you think of a red LED, if you look at it when it's turned off, it's not necessarily going to look red. But if you shine a red light on it, it will actually absorb that energy, at least some of it. Well, that's a problem in this situation, because we're talking about a lot of energy that you're dumping into that. And potentially you could burn out that element then, because it's absorbing all the energy and it doesn't want to. It wants to expend energy, not absorb it. So that's a problem. And the only way to fix it in this situation would be to make sure that they just never cross, so there's no overlap between the elements. That requires tremendously good precision for aligning these things. Alright? And it's also, even if you're not damaging the other elements, it still is you're losing energy because it's being absorbed and going somewhere else, somewhere other than producing thrust. Well, Generation 4 addresses some of these concerns. Maybe not perfectly, but it's also, like, canonically, they've only just been introduced in the Catherine version. So it's still multiple emission layers, just like Generation 3, but they are of different frequencies. So you have multiplied power, but it's potentially a weaker power. That depends. That's something you get it equal if you are balancing out the frequencies right. But the main thing is that because they are different frequencies, the elements themselves can actually be less expensive. Generally speaking, producing red light is cheaper than producing green light, which is cheaper than producing blue light, since I'm using red, green, and blue in the image here. And for anyone that remembers the early days of Blu-ray and the PlayStation 3, that's very true. Blue laser light, very hard to produce, very expensive. It got better, but for a time, no, it was very expensive. Now, technically, there's the issue that, while the elements cost less, the reflector does need to be more complex. That's for optimal efficiency, because, it reflects light, but technically materials can reflect different frequencies of light a little differently. Or it could just be that the light enters into the reflector and then it's going to be refracted a little bit, which will differ based on the frequency, and so it gets reflected out a little differently. Well, you make the reflector to handle that, so nope, it all will go in the same direction. Makes it more expensive. Potentially could drop away from that, but these things that I have in there, nope, they're real fancy, they're complex. But still is overall, even that added complexity could still be less expensive. Now, the precision alignment of the elements is removed now, because red and green are different colors. So the red light produced by one set of elements isn't necessarily going to be absorbed by the green, by the green elements. So the red can just go right through, can pass through, so there's no loss of energy, no risk of damage. And one example of that could be a microwave, right? So you've got that screen in front that prevents the microwave from coming out, but you can still see through it. So there's a light on in the microwave as well. So you've got two different frequencies of light, microwave and optical. Optical comes through, we can see through it, but the microwaves cannot. So it's kind of like that, where because the optical light, that's what we want to see. We want to watch the thing spinning round and round and round, and we want to watch that. Hey, sometimes it's boring. It's boring to look at anything else. So you're watching that, and that can come through. It has no issue. It'll just pass through the thing that's designed to capture the microwave. So that's kind of the idea there. And also means that packing tolerances for these elements in the engine can be looser. Because, yeah, it can be off by a little bit because, yeah, it's not going to interact. It's fine. So the overall cost is going to be much, much lower because of this change to the multiple different frequencies. And finally, we're at the end. Spaceship Building 101 is complete. The final is a third of your grade. Remember, I present this to college students. So I try to make some jokes. Now, there are some additional classes. Again, this is kind of a joke, but there's also a point here that I want to make. Space Station Building 151 is an additional class, which will cover basic station design, placement, and power. Spaceship Building 201, which will cover warp and other superluminal travel methods, generational ship design and concerns, as well as physical construction. And then Space Station Building 251 will cover advanced design, emergency systems, and atmospheric reprocessing. As I said at the beginning of this video, I do want to make specific videos for the different sections of this presentation, at least those specifically concerned with science fiction. Potentially I could do that for these topics as well. I am not committing to doing any of those. I'm just saying I potentially could, because each one of these I've had to give some level of consideration to. So I have had to think about, how do you design a space station? Where do you want to place it? How do you power it? I mentioned some of that earlier with fission and fusion, but even then there is some depth there as far as I get into, okay, this is where you would have the fission set up. You wouldn't have it over here. You'd have it here because this is a very important part of the station. It's it's the last refuge, so it makes sense you have the most stable power there. And there's other reasons as well, other benefits to it being there. Warp and other superluminal travel methods. I use warp. I find that the most reasonable and most easy to explain, but there are other methods. I could potentially do a video going into all that. I'm not committing to it. Please don't try to hold me to it. But I could go through other methods like wormholes or hyperspace travel, which have different variants that you will find in different science fiction. I go through why I think those are not as good as warp. And by good, I do mean the ability to explain it, the ability to make it reasonable, okay? So maybe I will do those videos. I don't know. We'll see. But it is still, each one of these I've had to consider. And I kind of want to talk about it. I like talking about this stuff. It's fun. All right. Now getting to the conclusion for writing. And I was correct on this, by the way. There was at least one person in that room that has the desire to write a story. I do kind of believe everybody wants to be a writer in some way. Everybody has an idea for a story that they want to tell. So I have here some tips that I've got based on my own experience. Which at this point is 5 novels. Okay, first tip, make notes. If you have an idea, write it down. Don't make yourself just rely on your memory, write it down. So that way you can come back to it potentially even years later. And it could be something random. It could be an idea for a full story, or it could be an idea for just a conversation in a story. And maybe you'll fit into that story, maybe you'll fit into this story. There's also, if you write it down, at least for me, I know when I'm writing it down, the exact wording that I use will be different than what I originally thought. But then as I'm writing it down, I'll start thinking about more. I'll start developing it more there, so I have a more complete idea that I can then come to later. Be critical of stories, good and bad. So that one, that is kind of right there. Just be critical of stories, analyze them, try to understand what makes a bad story bad and what makes a good story good. Or specific elements within a story. Do that because if you understand why, when reading a story, I don't like this. Okay, why don't you like it? This is why I don't like it. Good. Now you can avoid doing that in your own story. Versus, I like this story. Great. Why do you like it? This is why I like it. Good. Now see if you can apply that in writing your own story. It's kind of like that. Take that opportunity to learn from other people, from other stories, to make yourself as good as possible. Okay, and trust me, they're doing the same thing. Right? Any good writer, any good storyteller, they're going to pay attention to other stories to try to improve their own. Set a process. Okay, so this one may seem a little weird. But you know what? I actually have a perfect example right now that I can tell you. All right, besides my writing. This presentation, I obviously gave it when I actually delivered the presentation, but recording this is like the third or fourth time I've tried recording it, and I've changed my process for it to make it a lot easier and a lot more comfortable for me. I was getting so frustrated yesterday because I was doing it sitting down. All right, I'm sitting down a little bit cramped at my laptop trying to do all this. What am I doing now? I've turned the mic and I'm standing up because I made this presentation intending to be standing up, to be moving. Right? And it is so much more comfortable for me to do this. I feel much more comfortable doing it. And yeah, so that's a lot easier. I don't know if I will do this in the future. It's a long presentation, so that's also impacting this. Other videos hopefully will be shorter, so I can do it sitting down. It would help with being on camera, that I'm sitting. But it's just that, for right now, is my process because it's more comfortable and it's making it easier for me to get through this presentation. Now, while writing, I listen to music, and I listen to specific music, and I actually keep track of it. So I can tell you from previous story, what music did I listen to all the time when I was writing it, all the time when I was editing it, right? I have specific music. I basically have a soundtrack to the story. And the reason I do that specifically, so this is my rationale for my process. Music impresses emotions onto me and probably anyone, okay? Well, if I'm having that constantly impressed onto me, then that's going to help achieve a certain emotional stability throughout the work, all right, throughout my writing. And I find that valuable because I don't want the emotions of it to constantly swing back and forth because I did it one day versus another. I did it 1 week versus another. I was writing 1 month versus another, okay? Now, whatever your process is, figure it out and go with it. I mean, it's like, you're free to do whatever. I would stress this, though, because we're talking about a ritual as well. You're kind of ritualizing this to get yourself into a specific mindset. Keep it simple, okay? I'm very serious about this. Keep it simple. Because, personally, I don't suffer from writer's block. I've yet to run into that occurring for me, which I just consider myself very fortunate there. But maybe some people do. Well, is the process complex? Like the whole, I'm standing up. Maybe it's I'm standing up. I need to have my headphones on. I need to be listening to specific music while doing this recording. Okay, well, which headphones? I've got one pair of headphones that's really nice. Maybe that's the pair I gotta wear. But maybe I don't have them. Maybe I lost them, so I have to listen with another set of headphones. Oh, those don't feel right, so it's throwing me out. I can't do... Keep it simple. If you make it complex, then it's going to be harder to get into that mindset. And if you are in a rut, if you are in writer's block, those details that you're getting wrong you may start obsessing over them because, like, oh, that's why I can't get into my... Keep it simple. So that way it's easy to turn it on and potentially also easy to turn it off. And by the way, this is not just advice from me. I first heard about this same kind of thinking on the radio. They were talking about a baseball player whose father, when teaching him baseball, when passing it down to his son, the batting ritual, when you come up and you see the players, they scratch their head, they adjust to their hat, they pull on they tug on their gloves, they maybe take the bat and tap it against the plate in certain positions, they shimmy a little bit, and this is all what one player does, okay? Like, one player does all those things. Well, he also has a specific order to this ritual to get into the mindset of, I'm going to hit that thing out of the park. The father recognized, yeah, when they get stuck in a rut, they can't get out of it. It's too complex, right? They can't get into that mindset. So, son, here's what you're going to do. You're going to keep it simple. You're going to take that bat, you bring it up to your shoulder, and you know what you do? You just tap yourself twice on the shoulder with it. That's it. That's what the guy did. That's what this MLB player did. He would just tap himself on the shoulder twice, and that was it. That was his ritual. That was his process. Now he's in that mindset to hit it out of the park. And that's what they were talking about on the radio. That when he gets in a rut, he gets out of it so quickly because the ritual was simple. The process was simple. So yes, very much. Set a process, and this can apply for many things. Baseball, writing, everything else. but keep it simple so you can get into it, into that mindset much more quickly. All right, that was long enough on point 3. Let's get to point 4. Listen to the story. This one may sound weird, especially because it does sound a little bit like I'm insane. But I have actually had this experience of hearing things from my story. Where, sometimes it is just generically the story itself is like, you know what? Let's talk to this character. Let's go have this thing. Okay, let's do that. I don't have an objection to it. I'm the author. I'm in charge, but I listen. I'll listen to my story. But sometimes it's also the characters themselves that are like, hey, what do we do on this day? I don't know. What do we do on this day? I guess I'm going to have to find out. I guess I have to write it. And it's not that crazy. I mean, the voices stop once I finish the book. Yeah, I mean, it's just, I guess another way to put it is inspiration. Pay attention to that. And, for me, when the story is flowing nicely and when it is forming well there, then that inspiration is going to be very directed, going to be very specific. And pay attention to that. Now, ultimately, and this is very much what the next point is, write to your satisfaction. You are the author. It is your story. It is not somebody else's story. Whatever feedback you get from a real person or from a character, from the story itself, you're the author. If you feel you need to reject it, go ahead and do it. Go ahead and reject the feedback. Okay? That's fine. But still, accept the feedback and think about it and decide, you know what, can I keep that feedback? Can I use that feedback or can I not? Now, I should provide some background here. I am self-published. I do not have an editor. I do not have an agent. Both an editor and an agent, I've also never worked with any. Both an editor and an agent, part of their roles, and they are professionals at this, part of their roles is to give you feedback, okay? Now, you might want to take that feedback at a higher level than just asking a friend. Because as I said, they are professional. Maybe this is the reason no editor or agent would ever want to work with me. I would still feel free to reject their feedback if I think it isn't good, if I think it won't work. But it still is they are there to help you with this. So listen to their feedback, definitely. But fundamentally, it is your story. You need to write it to your satisfaction. And by the way, I do have one story that I wrote that, yes, I'm satisfied with it. I don't think it's a good story. I don't recommend reading it. I really don't. But I'm satisfied with it because I know I couldn't really do that better. I tried an experiment, tried a genre that I'm apparently not skilled enough to do. That's fine. There's nothing wrong with that. And that's also kind of a point here. Write to your satisfaction. You can be satisfied with the story and be like, yeah, it's not good. All right, well, you can still put it out there. You can still self-publish it. Nothing wrong with that. And who knows? Maybe you're wrong. Maybe somebody else will really love it. But it still is. You can get to that end and be like, yes, this is a story. I've told the story. And then you can move on. All right, so now let's get into a few more practical tips, I guess you'd say. The software I use when writing, which this is a little bit outdated. Not much though. Microsoft Word or any word processor. I got Office on my desktop. On the laptop, I'm using LibreOffice, which its writer is comparable in features at least to Word. Some of the designs are different, which that's fun to learn. But still is. Word processors, they are nice. You know why? Spell check. Seriously, spell check is wonderful. It can sometimes fight you, where it's like, try and tell me, hey, that's not a word. Yes, it is. I'm serious. I've got one book where it's fine with this name for a character I use. That's a word. I can use that if I make it possessive, apostrophe S. It's then like, hey, this isn't a word. What are you talking about? How is this not a word, but the base name was? What? It made no sense. Anyway. Yeah, spell check is still very nice. Grammar check is garbage. So often it's like, hey, this is a fragment sentence. It's like, yes, I know. It's speech. It's allowed to be. Now shut up and get rid of that green squiggle. Because I'll still see it and it's like, I gotta try to fix this, don't I? It's like, well, no, I don't. This is fine. I'm rejecting your feedback word and I'm sticking with my own. Yeah. So word processor is great to write in. Now for actually constructing the book, the PDF that I would submit to Amazon or somewhere else, I use LaTeX for the print typesetting. LaTeX, it is so powerful. It's wonderful. I love it. It's got a learning curve though. I do still recommend trying to use it, especially if you are comfortable working in code. Because a simple way to put it that isn't completely accurate, but it gets there. In LaTeX, you are writing a program that compiles into a PDF. But the thing about working in source code like that, you have control over everything. You don't have that level of control in Word. There are things I can adjust in adjust in LaTeX I either can't do in Word, or it is buried behind so many menu layers that it doesn't do it. It does do it, but it's just hard to get there. And same thing with LibreOffice. Sometimes LaTeX is just easier because I can just put in a single line of code and it works. Or I look it up and I find a single line of code that works, or I make some adjustments there. But still, it is so nice, so powerful. Now for version control, I'm using Git now. I used to use just the track changes feature in Word, and it is also in LibreOffice. But it's kind of garbage in both, because it's only one layer deep. So you write your first draft. Awesome. Going back in and editing it. Track those changes so I can undo it. Okay. Go through and make that first editing pass. Great. You're on 1.1. Now I want to go back in and do 1.2, and I cannot separate changes from 1.2 from 1.1. Because as I said, one layer deep. This is where Git comes in. Git is designed for tracking any changes as you want to make. And it can even be separated out. So with LaTeX, as I said, you're basically writing in source code. Git is designed for working with source code, so it works very nicely with that. Not so well with the docx format, because that's actually compressed already. So it's you can make your Git repository very large. So it's getting kind of technical there. But Git is still very nice because there's basically an unlimited depth of changes. So I can go back for I've only been using it for one book so far, but I'm going to use it going forward. I can go back to see chapter 2 in the first draft. I can also see it at version 1.1 and 1.2, 1.3. The published version was 1.4. I can go back and I can see those changes very easily. And it's just labeled very nicely. And one thing that I was kind of trying to get to with LaTeX, I keep every chapter in its own separate file. That also helps with keeping track of these changes. And I would also say if you're going to work in LaTeX or another code, like a Markdown or HTML, which HTML is actually relevant for the next point, try to have every sentence on a separate line. Again, it helps with finding changes in Git. Git will highlight every line that's changed. You can have it do every word, but it'll highlight every line that's changed. Well, if every sentence is a separate line, it makes it a lot easier to find the specific one that you made a change to. Now, lastly, for the EPUB creation, I use Sigil. Okay, it's not, well, for my uses at least, it's not that fancy. I'm not throwing in a whole bunch of images and graphics and all that, so it's not that bad. But it works very nicely. But what is an EPUB? An EPUB is basically a specially constructed website. No, seriously, you're putting HTML in there, which is why I mentioned HTML earlier. Working directly in HTML might not be a bad idea. And then I just put it into Sigil, all the separate files. It composes it into that EPUB that then I can submit to Amazon to make for the Kindle or another place. I am, as I said earlier, I am self-published and I have been using the Kindle Developer Program since I started. But there's others. Barnes & Noble has theirs. And I'm certain that you can also self-publish on various other places as well, especially electronic versions. Barnes & Noble and Amazon both have the ability to print out the physical copies, which is where LaTeX comes. All right. Oh yeah, one last thing I want to mention about Sigil, about Git, about LaTeX, and about LibreOffice. This isn't true of Microsoft Office, unfortunately, but true of those other four, they are all open source, and they're all free, okay? So this is a great time to be a writer, because you can, if you have a computer and you have an internet connection, all the software you need to write the story with spell check, to make the print version, to track changes, and to make the electronic version. Everything you need for that, it's out there and free. You can just download it and get to it. I mean, yeah, some configuration, but still, it's all there. That's awesome. It is so radically different than decades ago when it's like, you need to either write out by hand, which means you need a lot of paper, so you need to be buying that, pens and pencils, you need to be buying all that, you need to mail it out somewhere. It's like, no, you can do this all, you can make it all right there, and you just submit it somewhere, and if somebody buys the print copy, then it's printed on demand. If somebody buys the electronic copy, well, electronic copy, not company, electronic copy. If somebody buys that, it just gets downloaded to the device. It's a great time. I just wish more people read today. But it is, as far as creation, it will only get better from this, and right now it's already great. So yeah, and that really does end this, because all I got left are just the references. I've had the citation notes throughout the presentation, so yeah, here are the slides for those. And yeah, I'll think about it. It depends on if I remember, really, to put like the links in the description so you can find it yourself. So you can find it that way. But yeah, so that's it. And I don't know what video will be next. This was the inaugural one. Don't know what number 2 will be, but hey, I'll see you then.